Welcome to a capstone event in this course. We are going to prove Rabin's probabilistic primality test, which basically says that Miller's primality test that we already have talked about, which is actually a test to detect composite numbers, has only a limited number of false positives within the pool of bases that we can use to test. We will talk about that in more detail, of course, once we actually restate the whole thing. We need to set a little bit of groundwork first, because we have to talk about what basically is like logarithms in modular arithmetic, and that's what we'll start with. Okay, so basically these indices for index arithmetic, they play the role of logarithms modulo n. And so that also means that even without Rabin's probabilistic primality test, they're a natural next step as we are investigating modular arithmetic, because it's another piece of regular algebra that we'd like to carry over. We will use these indices to determine which numbers are power residues, and power residues, these things here, are basically just nth powers modulo m. And the theorem that we will have will only work when there are primitive roots modulo m, but that'll be just fine because we're going to do everything else in modular arithmetic, modulo primes and prime powers. And well, Miller's primality test then basically fails to detect the number as being composite when certain power equations are solvable, namely b raised to a certain power equals to -1. And so the investigation of power residues will lead us to counting how many solutions such an equation can have, and that'll give us Rabin's probabilistic primality test. And we'll then at the end also talk about a few more primality tests as we slowly try to disengage from this pretty deep result, as far as I can see, for number theory, because we're going to use, to prove Miller's test, to prove Rabin's probabilistic primality test, we're probably going to use just about everything we've proved up to now, either directly or indirectly, in that we're going to use results that are derived from that. Okay, well, let's go. If we have two natural numbers, a and m, so that there is a primitive root r modulo m, and so that the greatest common divisor of a and m is 1, then we will call the unique integer x between 1 and phi of m, so that r to the x is equal to a modulo m. That number will be called the index, or the discrete logarithm of a to the base r modulo m. So that is exactly how we would want to define or exactly how we have defined logarithms in regular algebra. The logarithm is an exponent that makes a certain thing happen. We are going to use similar notation, except that we call it the index, not the logarithm. So it's called index of a to base r. And we're assuming that the underlying modulus is fixed. That'll require a little bit of thinking, because actually what's going to happen, because of this result that we have, that a to the I is equivalent to a to the j modulo m if and only if I is equivalent to j modulo phi of m under the right conditions. That result says that when we pull the exponents down, our modulus also will change from m to phi of m. We're going to see that. Okay, so as an example, well, 2 is a primitive root modulo 11, which means that 2 to the 10th is the first power that's equivalent to 1 modulo 11, and that'll mean that we can compute indices to the base 2 in modulo 11 arithmetic. Well, let's make sure that 2 really is a primitive root modulo 11. We can just count along, right? 2 times 2 is 4, times 2 is 8, times 2 is 16, which is 5 modulo 11, times 2 is 10, and so we have 2 to the 5th is equal to 10 modulo 11, and the order of 2 has to be either 2, 5, or 10. It's neither 2 nor 5, so the order of 2 modulo 11 is 10, and that means it really is a primitive root modulo 11. And well, so now, for example, since we can compute indices, the index of 10 modulo with respect to base 2 is 5 in modulo 11 arithmetic, because we've just counted our way through that, and we had seen that 2 to the 5th is equivalent to 10 modulo 11. Okay, well, let's take a look at some theorems. if we have a natural number so that r is a primitive root modulo m, so that basically just helps us sidestep the a little bit more cumbersome result that tells us when there is a primitive root. We just say m is one of those numbers. And we take a and b to be integers so that the greatest common divisor of a and m and the greatest common divisor of b and m is 1. Well, then the index of 1 with respect to base r is equivalent to 0 modulo phi of m, not modulo m, modulo phi of m. The index of ab to base r is the index of a to base r plus the index of b to base r, again modulo phi of m. And for all natural numbers, we have that the index of a to the k to base r is k times the index of a to r to base r modulo phi of m. And that is, of course, exactly like the logarithm laws that we know, except that we have to go in modular arithmetic and that our modulus is phi of m. And, well, we're going to see why in just a second. And, well, it's very simple, right? R to the phi of m is equivalent to 1 modulo m. And because no smaller positive power of r is congruent to 1 modulo m, the index of r of 1 to base r is equivalent to 0 modulo phi of m. R to the index of a to base r plus index of b to the base r, well, we take that apart. That's r to the index of a to the base r times r to the index of b to the base r, which is a times b, which is r to the index of ab to the base r modulo m. And so we have r to one exponent is equivalent to r to the other exponent modulo m. And we had an earlier theorem that said when that is the case, then the exponents must be equal, but the exponents must be equal with respect to modular arithmetic modulo phi of m, not modulo m anymore. And that means that the next result should work very similarly, right? R to the k times the index of a to base r is r to the index of a to the base r raised to the k. That's a to the k, and that's, of course, r raised to the index of a to the k to base r all modulo m. And again, we cancel the bases and get that the index of a to the k to base r is equivalent to k times index of a to base r modulo phi of m. And yep, that's it. So we've got logarithm laws. And how are they applied? Well, in exactly the same way as before, except that now we have to mind all the other things that we know about modular arithmetic and how to cancel things. So if we want to solve, for example, the equation 3x to the x to the fifth equivalent to 8 modulo 11, well, we set it up and we take indices / logarithms on both sides, just like we would otherwise. And we take the index to base 2 here because we know that that's one where we can take the index. Then we apply, and we note that as we do that, as we take the index, the arithmetic changes from modulo 11 to modulo phi of 11 because we've pulled down exponents here essentially. And well, phi of 11 is 10, so everything we do from here on is modulo 10. The index of 8 to base 2 is 3 because 2 cubed is 8. And here we're using the index laws / logarithm laws. So this is the index of 3 plus 5 times the index of x. And well, the index of 3 to base a apparently is 8. So that is a slightly uglier computation. Let's count that through. 2 times 2 is 4, times 2 is 8, times 2 is 16, which is 5 modulo 11, because the index is still computed modulo 11. So we end up with 5. 5 times 2 is 10. 10 times 2 is 20, which gives us 9 modulo 11. Times 2 is 18, which gives us 7 modulo 11. And if you multiply that by 2, you get 14, which is 3 modulo 11. And if you've counted all the 2's with me, you realize that this was 2 to the 8th here. Okay, so that works out. Right-hand side, of course, is still 3 modulo 10. And so now we need to subtract 5 modulo, well, we need to subtract 8 modulo 10. That's the same as adding 2, so we get 5 index of x to base 2 is equal to 5 modulo 10. Here's where we're going to cancel the 5's, and of course, we are very much used to doing that because we've done a lot of arithmetic modulo prime numbers now, but 10 is not a prime number. So remember, the actual result is that if we cancel a number on both sides, we also cancel the greatest common divisor of that number with the modulus. So here we're canceling the 5 out of the modulus. And it turns out that the index must be 1 modulo 2. And that, of course, means that the exponent must be 1, 3, 5, 7, or 9, which means that x will be 2, 2 cubed, 2 to the 5th, 2 to the 7th, or 2 to the 9th. And if you work that out, you get 2 times 4 is 8, because we're now upping in steps of 2 to the 2, right? And we're going module 11, so let's see, 8 times 4 is 32, which is 10 modulo 11, 40 is 7 modulo 11, and 7 times 4 is 28, which is 6 modulo 11, so these are the results. And we're not going to talk our way through the rest, but as I just looked at those slides one more time before I actually launched into the presentation, I double-checked plugging in all these numbers and realized that what happens is basically you always end up with exponents that are 2 to the some number times 10 plus 5, and then the sum number times 10 goes away because 2 to the 10 is 1 modulo 11, and then everything else works out very quickly to show that it is equal to 8 modulo 11. So that's something that I'll leave to you. Now we talk about power residues, and if you've got two positive integers, and a so that the greatest common divisor of a and m is 1, then a is a kth power residue of m if and only if there's an x so that x to the k is equal to a modulo m. So basically that means if k is equal to 2, a is the modular equivalent of a perfect square, and otherwise it's the equivalent of a perfect kth power. And once we have that, we can figure out when we get those. So again, we take mk, be natural numbers, a be an integer, so that first of all there is a primitive root modulo m, and we want also again that the greatest common divisor of a and m is 1. We let d be the greatest common divisor of k and phi of m, and then there is an x so that x to the k is equivalent to a modulo m if and only if a to the phi of m over d, which is an integer, is equivalent to 1 modulo m. So this is actually really nice because the solvability of a power equation is completely determined by something that's a lot simpler, namely taking the right hand side and raising it to a power. Yeah, that shouldn't be too bad then. Okay, moreover, there are solutions, or if there are solutions, then they're exactly d-incongruent solutions modulo m. Well, we're going to see that in the proof also. So, proof. Well, if you take x to the k equivalent to a modulo m, that's equivalent to, well, apply the index laws, apply the logarithm laws. K times the index of x to base r is equivalent to the index of a to the base r, and that is all modulo phi of m. And this linear congruence, because if we now consider the index of x to the base r as the variable, as I'm saying here, that linear congruence has a solution if and only if the greatest common divisor of k and the modulus, which is phi of m, divides the right-hand side, which is the index of a to the base r. So that already is nice. But the indices are potentially hard to compute, so now we want to change that to the condition in the theorem. Because in this case, well, okay, there are d-incongruent solutions modulo phi of m, that gives us the moreover part. And those translate into d-incongruent solutions x modulo m, because we just put the indices back into the exponent, right? And then finally, we want to translate this d divides the index into something that is a bit simpler. And well, so what do we note? We note that d divides that index if and only if phi of m over d times the index is equivalent to 0 modulo phi of m, and that's because I can take this denominator and stick it under the index and get an integer multiple of phi of m out of it, right? And yeah, that is vice versa. And that's the case if and only if, well, if I have a to the phi of m over d if that actually is divisible by the index of a to the base r, then that ends up being equivalent to 1 modulo m, and vice versa. And so that takes care of the existence of power residues. As an example, well, if I wanted to solve the equation x cubed equivalent to 4 modulo 9 if possible. Well, okay, I say proof here, I guess I should have just said computation, but what do we have to do? We have to take the right-hand side, raise it to phi of the modulus, and divide by the greatest common divisor of the power and phi of the modulus. Well, so phi of 9 is 6, so we have 4 to the 6 over the greatest common divisor of 3 and 6, and the greatest common divisor of 3 and 6 is 3, so we end up with 4 squared. 4 squared is 16, which is equivalent to 7 modulo 9, and therefore there is no solution, because 7, of course, is not equivalent to 1. Okay, that's already it regarding the power residues, and now we're going to start talking about Rabin's probabilistic primality test, and the first thing we need are a couple of lemmas regarding solvability of various types of equations. So, we take E, Q, P, all natural numbers, and we want P to be an odd prime number. Then we claim that the number of pairwise incongruent solutions of the equation x to the q equivalent to 1 modulo P to the E is the greatest common divisor of q and P to the E minus 1 times P minus 1. And even though this, of course, now looks a little bit different, it actually comes out of the result that we just had, because this is phi of P to the E, and so the greatest common divisor, then that sounds and feels very similar to what we just did. And, well, here we go. Because P to the E is a prime power, there is a primitive root R modulo P to the E, right? That's something that we must not forget, because it is not always the case that there are primitive roots. And, well, that means we can apply the preceding theorem with A equals 1. And because any power of 1 is 1, the condition in the theorem is satisfied and the congruence has a solution, because the condition in the theorem was that the phi has to be, we take A, which is 1 raised to phi divided by some divisor of phi, so it's 1 to an integer power, so all that works out. So there is a solution, and because there are solutions to that congruence, again by the previous theorem, there are q, greatest common divisor of q, phi of P to the E, pairwise incongruent solutions, and that greatest common divisor is just the greatest common divisor of q and P to the E minus 1 times P minus 1. Good. Now, what does that tell us here? If we try to look a little bit ahead, these kinds of equations are part of what needs to be satisfied for Miller's test, of course, and if we're already saying that we're limiting here the number of pairwise incongruent solutions, that will ultimately limit the number of bases for which Miller's test could be passed. Okay, now we've got one. Yeah, that's one of those results that I really like, because there's a bunch of letters to remember, so let's see if we can work our way through that. So let's P, capital N, K, T, S, and U be natural numbers, so that P is an odd prime number, so that P minus 1 is 2 to the S times T, and T is odd. So let's make sure that this becomes a bit more natural. When you've got an odd number, P minus 1 is even, and for an even number, it is very natural to say that we want to break that into a power of 2, which is 2 to the S, times an odd number, which is T. And we also want to do the same thing with N. And so we split off all the powers of 2, and then U is the odd number that remains from the N. And we claim that the number of pairwise incongruent solutions of x to the n equivalent to -1 modulo P is 2 to the k times the greatest common divisor of T and U, as long as 0 is less than or equal than k is less than or equal than S minus 1, so as long as not too many powers of 2 are hidden inside N. And that number is 0 otherwise. And so again, if you've already looked up Miller's test, which may have been a good idea at the beginning, and we're also going to recall Miller's test in a panel later on. Maybe I should have shown that earlier, but in Miller's test we also have to solve, for Miller's test to deliver a false positive, equations or equivalences of this kind must also have solutions, namely that base must satisfy that. So again, if we can somehow get a handle on the number of pairwise incongruent solutions of these things, we're limiting the number of possible bases for which Miller's test will work. Okay, proof. Well, take R to be a primitive root modulo P, so again we need to make sure that we recall that P is prime, so that primitive roots exist. And then you take the equation x to the n equivalent to -1 modulo P. Well, that's equivalent to n times the index of x to base R, being equivalent to the index of -1 to the base R. But the index of -1, even though at first looks kind of funny for us, well, we know that R to the P minus 1 for a prime number is equivalent to 1. And we know then also for a primitive root that R to the P minus 1 over 2 can't be plus 1 also, so it's got to be minus 1. And so the index of R of -1 mod to the base R modulo P is P minus 1 over 2. And that's, of course, again, modulo phi of P. And n was 2 to the ku index of x to the base R. That would have to be equivalent to P minus 1 over 2 is, with this one being 2 to the st, is 2 to the s minus 1 times t. And we're still looking at modulo phi of P, and phi of P is P minus 1, which is 2 to the s times t. And that congruence has a solution if and only if the greatest common divisor of 2 to the k u times 2 to the s t, right? Again, we're looking at a congruence where we're solving for the index of x as the variable. That thing has a solution if and only if this greatest common divisor, which happens to be easily verified, is 2 to the minimum of k and s greatest common divisor times the greatest common divisor of u and t, if and only if that greatest common divisor divides 2 to the s minus 1 times t. And that means in particular that s must be between 0, that k must be between 0 and s minus 1, because otherwise, if k was equal to s, then this would be 2 to the s here, and that does no longer divide 2 to the s minus 1. So we must have that k is between 0 and s minus 1, and otherwise we have 0 solutions. So we only have solutions when that is the case. And we keep going, and we know that in this case we have 2 to the ku, 2 to the st, greatest common divisor, which, now that we know that k is less than or equal to s minus 1, is just 2 to the k times the greatest common divisor of u and t, incongruent solutions modulo p. And we move on. One more lemma, and that one is actually fairly simple, even though I wanted to spell it out one more time because it's this implicit application of the Chinese remainder theorem. I'm not sure if this just reveals that I'm not terribly good at keeping track of these things or if it's normal, but let's just spell it out one more time. We will ultimately look, of course, at a number that is composite, so we take n to be a product j equals 1 to r pj to the ej, and we suppose that the congruence f of x equivalent to 0 modulo pj to the ej has kj incongruent solutions modulo pj to the ej. Well, then the congruence f of x equivalent to 0 modulo n has product j equals 1 to r kj incongruent solutions modulo n. And moreover, every solution of this congruence solves all the other congruences because, of course, pj to the ej divides n. So if n divides f of x, then pj to the ej will also divide that. So that one is not that hard, but what it basically says then is that every solution modulo n really is obtained from the solutions of the other congruences. I think that is really just restating the Chinese remainder theorem, and now that I've done number theory for a little bit longer and gone through all these things, it feels a lot more natural to me. But as I was making those slides, I thought, okay, now let's talk our way through this just one more time, just to make sure. And it was really for my own sake too, and I'm not ashamed to say that either. Okay, so proof. Well, if you take a solution of f of x equivalent to 0 modulo pj to the ej, and you do that for j equals 1 to r, then by the Chinese remainder theorem, the system of congruences x equivalent to yj modulo pj to the ej has a unique solution y modulo n, which is the product of all those pj's to the ej. But then every pj to the ej divides f of y, because f of y was still equivalent to yj modulo pj to the ej, which means f of y is equivalent to 0. And, well, that means, because the pj's are all pairwise distinct prime numbers, that f of y is equivalent to 0 modulo n. So that means that every one of those y's is a solution, and because we can set up product j equals 1 to r kj such congruence as we obtain that f of x is equivalent to 0 modulo n, that congruence has exactly that many, namely product j equals 1 to r kj incongruent solutions modulo n, or has at least that many solutions. And then the claim that every solution of the congruence modulo n is a solution of all the congruences modulo pj to the ej. That's of course trivial, but it does show that all solutions of that congruence are obtained as indicated above, and that means that the congruence modulo n really has exactly product j equals 1 to r kj incongruent solutions modulo n, and that will be important as we are now solving congruences modulo what will be a composite number. So, what was Miller's test? Maybe I should have put that panel before I started the whole thing. But Miller's test started with something that said Fermat's test delivers what could be a false positive or a correct positive, and that is, okay, it would be a false positive in case n really is composite, but suppose b to the n minus 1 is equivalent to 1 for the greatest common divisor of b and n being equal to 1 for an appropriate base. And then we recall that if n is prime, then b to the n minus 1 over 2 is plus minus 1 modulo n. And so now if n is an odd integer and n minus 1 is 2 to the s times t, this, I think, pretty much canonical way to write down an odd number, power of 2 times an even number, power of 2 times another odd factor. So t to the st with t odd. Then we say that n passes Miller's test for the base b if and only if b to the t is equivalent to 1 modulo n, or b to the 2 to the j times t is equivalent to negative 1 modulo n for some j from 0 to s minus 1. And basically what we are doing is we actually have to look at this backwards. We're starting with b to the n minus 1 equals 1, and we just keep taking square roots. And as we do that, of course, the exponent for the 2 here declines to s minus 1, s minus 2, and so on, all the way down to 0. And all the way there, as long as, if p was a prime number, then the only roots we could get are plus or minus 1. And that is why prime numbers pass Miller's test. And however, a composite number could also pass it. It's just that if a composite number at some stage just doesn't spit out the right numbers, then the composite number is recognized as composite, and that is Miller's test. Okay, so now the theorem is that if n is an odd composite integer, then n passes Miller's test for at most n minus 1 over 4 bases b in the set 1 through n minus 1. Okay, proof. Well, so let n be the product of pj to the ej. Let that be a composite number that passes Miller's test for a base b. That'll mean that b to the n minus 1 is 1 modulo n. It'll mean that n minus 1 is 2 to the st for an odd number t and s greater or equal than 1. And it'll mean that b to the t is equivalent to 1 modulo n, or b to the 2 to the jt is equivalent to negative 1 modulo n for some j from 0 to s minus 1. Okay, now one of the earlier lemmas says that x to the n minus 1 equivalent to 1 modulo pj to the ej has greatest common divisor of n minus 1 pj to the ej minus 1 pj minus 1 incongruent solutions. Well, now we note that the greatest common divisor of n minus 1 and pj to the ej minus 1 times pj minus 1 is actually the greatest common divisor of n minus 1 and pj minus 1. And that is because pj is a factor of n, which means if pj was part of the greatest common divisor of something that involves n minus 1, then that would be a prime number that divides n and n minus 1, and that doesn't work because no prime number divides 1. So that means that the greatest common divisor cannot have any factors pj, and that means it's got to be just the greatest common divisor of n minus 1 and pj minus 1. Hence, by the Chinese remainder theorem, the congruence x to the n minus 1 equivalent to 1 modulo n has exactly product j equals 1 to r, n minus 1 pj minus 1 incongruent solutions. And now, well, now we will consider 3 cases for the number n being the product j equals 1 to r pj to the ej. Namely, there is the case that one of the ek's is greater or equal than 2. Then it's possible that all the exponents are 1, and we're going to also then near the end assume that r is greater or equal than 3, and that's just to make the last estimate work. The bulk of this argument here for all ek being equal to 1 will also, of course, work when all ek are equal to 1 and r is equal to 2, and that'll be our final case where we have to finagle things a little bit more. Alright, so proof for case 1. Well, case 1 is that there is a case so that ek is greater or equal than 2. So we just look at the product from j equals 1 to r, n minus 1, pj minus 1. So that's just an estimate for the number of solutions of that first test that we do, b to the n minus 1 equivalent to 1. And, well, the greatest common divisor of two numbers is certainly less than or equal than either of the numbers. So this is less than or equal than the product of the pj minus 1. And now, well, every one of the pj's is pj minus 1 is less than or equal than pj. And that's fine, except that we want to treat pk separately, because that's where we've got a good exponent, right? So pk is not kept in this product, pk is kept out here, and we keep the pk minus 1. And all we're doing is we are dividing by pk to the ek and multiplying with pk to the ek. Well, what do we know? Well, okay, we keep the product, we keep the pk to the ek, and because n is an odd number, all the prime factors of n are odd, and so the smallest prime factor here would be 3. So we get, in the exponent for 3, we would get 2 divided by at least 9. And it can be verified that if you go to larger prime factors like 5, well, you get a 4 up here, but you get at least a 25 in the denominator. And so that means that, or that doesn't mean, but it is something that you can then work out, that as your numbers increase, yeah, your numerator increases linearly, your denominator increases quadratically, but you end up with something that for all the pk's, this is smaller or equal than 2/9. And now this product, it turns out we keep the 2/9 and we realize this is the product of pj's times pk to the ek. Even if ek is the only exponent that is greater or equal than 2, this product times the pk to the ek will be less than or equal than n, so this is less than or equal than 2/9 n, which is less than or equal than n minus 1 over 4, where we assume that n is greater or equal than 9 in the last step, if we want to be absolutely careful that this really works for all n. And here's probably where I need to say something real quick, and that is, yeah, by training I'm an analyst, so when I look at an inequality such as 2/9 n less than or equal n minus 1 over 4, I automatically assume n is large enough for that to work out. And so, yeah, I had to double check, and you can double check that it only starts working with n greater or equal than 9. And that is really also what is ultimately correct, of course. But what we certainly also would want to see here is that this is a test that is only interesting for large numbers. So even if this test would start working only for n greater or equal than 500, hey, that's still plenty. There's a little bit of a difference in approaches here between analysts and number theorists, because number theorists, of course, have to make sure that stuff works out exactly. An analyst, yeah, get an inequality for n large, that's perfectly fine. And so then what also is probably happening right here for you is that all of a sudden, this is a change in gears, right? We have not worked with inequalities very much in this course. And it's kind of interesting. I've mentioned before, and you're sick of it by now, yeah, I'm not a number theorist, I only play one on this show, but when I started seeing these proofs, I was breathing a sigh of relief, because I've worked with inequalities for a long professional career by now, so that was just like, oh, okay, I know how to do it. All right, so be very careful here, because if you aren't as accustomed with analysis as to the point that these inequalities come naturally for you, you probably have to go through those very slowly and very carefully. But, I mean, that's just like going slowly and carefully through all the other arguments. Okay, we move on to case 2. And yeah, okay, so quick conclusion here. There are at most n minus 1 over 4 bases for which n is a strong pseudo-prime to the base b in this case. And that's going to be the conclusion for every single one of the other cases also, so we're not going to keep saying that. So, case 2. Case 2 is that n is a product of prime numbers where no prime factor is repeated, and we have at least 3 prime factors, and for just about everything on this panel, r greater or equal than 3 will not be used. So What we need to do now is we need to dig a little bit deeper. We let Sj and Tj be natural numbers, so that Pj minus 1 is 2 to the Sj Tj with Tj odd. And we assume without loss of generality, we can sort these things any way we want. We assume without loss of generality that S1 less than or equal S2 all the way through Sr. Yeah, sure, we can do that. Then the greatest common divisor of n minus 1 and Pj minus 1 is 2 to the minimum of S and Sj T and times the greatest common divisor of T and Tj, because of course n minus 1 is still 2 to the S times T. And by earlier lemmas, namely the lemmas that we just did as we switched to the section for Rabin's test, we have that now x to the t equivalent to 1 modulo Pj has greatest common divisor of T and Tj incongruent solutions. And x to the 2 to the kt equivalent to 1 modulo Pj has 2 to the k times greatest common divisor Tj incongruent solutions as long as k is less than or equal than Sj minus 1 and no solutions otherwise. Okay, so that was the two lemmas summarized. So we have to dig a little bit deeper, right? In the first case, we only needed to look at base raised to the n minus 1, and we got that in that case things work very nicely. Now that the case gets more complicated, we need to look at the other congruences that are required to be satisfied by Miller's test. And hence, via this Chinese remainder theorem lemma that I spelled out explicitly, there are product j equals 1 to the r greatest common divisor of T times Tj incongruent solutions of the congruence x to the t equivalent to 1 modulo n. And there are product j equals 1 to r 2 to the k greatest common divisor of T and Tj incongruent solutions of x to the 2 to the k times t equivalent to negative 1 modulo n, as long as k is between 0 and S1 minus 1, because as soon as it doesn't work for S1, it's not going to work for any of the, it doesn't work for one of the primes, and then we can't combine things into an overall solution anymore. So that works for k less than or equal S1. That is really indicated. That's not supposed to be an Sj or anything like that. And there are none otherwise. Okay, so the number of integers b for which n is a strong pseudoprime to the base b, which is of course another name for numbers that are composite and satisfy Miller's test, that number is at most, or even if, okay, here's again, being an analyst, it's at most that, and if it's exactly that, it doesn't matter because we need an upper bound. So that number is the number of solutions of the congruence with x to the t, plus the number of the solutions of the congruences with x to the 2 to the k times t. Okay, and those numbers are written up exactly here, right? Product j equals 1 to r, greatest common divisor t and tj, plus the sum k equals 0 to s minus 1, product j equals 1 to r, 2 to the k, greatest common divisor t and tj. First thing we notice is that the product of the tj's doesn't depend on k, so we can pull that out. So this is actually the product j equals 1 to r, greatest common divisor of t and tj, times 1 from here, plus the sum k equals 0 to s1 minus 1, 2 to the k, times r, because basically we keep having factors 2 to the k. We've got r of those things, so if I keep that inside, which I have, right, this is 2 products. It's the product of the 2 to the k's times the product of the tj's, and I'm only pulling the product of the tj's out. So the product of the 2 to the k's from 1 to r is 2 to the k to the r, which is 2 to the kr. Now this is really nice here because this is just a geometric sum. So this is the product j equals 1 to r, t, greatest common divisor of t and tj, 1 plus 2 to the r s sub 1 minus 1 divided by 2 to the r s minus 1, and that's because the summation formula would give us 2 to the r to the s1 minus 1 plus 1, and then the plus 1 minus 1 or minus 1 plus 1 of course cancel. And well, now we can do some algebra, or we can actually do some estimation, and that is, yeah, sure, I mean the greatest common divisor of something that involves tj is less than or equal than the tj, so this is less than or equal than the product of the tj's. And then I can multiply every tj with a 2 to the sj, but I don't want to do that for free. I want to divide by the same product, and of course the product of the 2 to the sj's is just 2 to the sum of the sj's. That's just elementary algebra, and the product back here is just the same as before. And so now, well, now we can say that this numerator here, well, this is 2 to the sj tj, so that's just pj minus 1, so this is the product of the pj minus 1s, perfectly fine. And the denominator here, because remember that the s1 was the smallest one, the exponent is greater than the sum of the, than if I just sum sj, so the exponent is greater than r times sj, which means the denominator is greater than 2 to the r s1. Okay, the exponents are greater than s1, so the sum is greater or equal than when I sum a bunch of s1, so the exponent is greater or equal than r s1, and that means that the denominator is greater or equal than 2 to the r s1, and of course if the denominator here is greater or equal than the denominator here, then the fraction here is less than or equal, as we want, than the fraction over here. This part, again, you can see here, I'm approaching that very much like I would approach analysis. I'm just looking at the stuff for which I've proven inequality, and the rest I know, yeah, it's just copied down. Okay, so that, well, what does that mean? Well, that is less than or equal than phi of n. Well, okay, that's exactly phi of n here, right? It's the product of the pj minus 1. And I'm pulling in the power, so I think this may in fact be equal, but if it's equal, it's also less than or equal, so there's no mistake here. And if I pull in the division, I get 1 over 2 to the r s1, which is here. And then I get the 2 to the r s1 minus 1 divided by 2 to the r minus 1, which is here. And then just a 2 to the r s1 in the denominator. Okay, so now we puzzle that apart a bit. Keep the phi of n, keep the 1 over 2 to the r s1. 2 to the r s1 divided by 2 to the r minus 1 times 2 to the r s1 is just 1 over 2 to the r minus 1, and then I've got a minus 1, and that's exactly that one, divided by the denominator. So again, yeah, that's equal, but less than or equal doesn't make it false. And, well, now phi of n, of course, phi of n is always less than or equal than n minus 1, so now we really have an inequality. The 1 over 2 to the r minus 1 is kept right here. And if I put this one and that one on the same denominator, I get 2 to the r minus 1 in the numerator here, and I subtract this one, so I get 2 to the r minus 2. And the denominator stays the same, and now I can factor out a 2 there, so now this is less than or equal to, yeah, okay, less than or equal to, what do we have here? That goes very quickly. N minus 1 stays. 1 over 2 to the r minus 1 plus 2 to the r minus 2 divided by 2 to the r minus 1 over 2 to the r s1. Here's what we're using, that r is greater or equal than 3 as far as I can see, because what we end up with then is that we have that this right hand side here is that this summand here is less than or equal than an extra 1 over 2 to the r minus 1. So that would basically mean that 2 to the r minus 2 is less than or equal than 2 to the r is 1. Yeah, that doesn't yet need r greater or equal than 3, because of course this power here is less than or equal than this power here, even in the worst case when s1 is just 1. Okay, so that continues. And of course 2 over 2 to the r minus 1 is less than or equal than 1 over 2 to the r minus 1. And now we're using, here in this very last step, we are using that r is greater or equal than 3, because that means that the denominator here is at least 4. And that takes care of the case that r is greater or equal than 3, which means what we have left is that r is equal to 2, that n is the product of two prime numbers, neither of which is raised to a power larger than 1. And notice, like I just said, that r greater or equal than 3 actually was really only used until the last step of this case 2. And that means with the same argument and notation as in case 2, we obtain that the number of integers b for which n is a strong pseudoprime to base b, so for which n passes Miller's test with base b, is at most n minus 1 times 1 over 2 to the s1 plus s2, 1 plus 2 to the 2s1 minus r divided by minus 1 divided by 2 squared minus 1. Just pull that last slide up one more time and realize that if we plug in r equals 2, that estimate is valid. And now we're just going to play with those numbers a bit, because this is, well, now we're actually doing equality, so n minus 1 is kept. If I factor a 2 to the 2s1 out of 2 to the s1 plus s2, what I end up with is 2 to the s2 minus s1. And the part in the back here, yeah, I just used some very sophisticated math to realize that 2 squared minus 1 is 4 minus 1, which is 3. So nothing much happened here. That is n minus 1, 1 over 2 to the s2 minus 1, 1 over 2 to the 2s1 here. I pulled that out because I want to pull this inside here. So I get 1 over 2 to the 2s1 plus 2 to the 2s1 over 2 to the 2s1 times 3 is 1/3, minus 1 over 3 times 2 to the 2s1. And that's n minus 1, 1 over 2 to the s2 minus s1. I keep the 1/3, and if I've got 1 minus 1/3 here, right, if I just disregard the common factor 1 over 2 to the 2s1, I end up with 2/3, so 2 over 3 times 2s1, that's just computed directly. And that is n minus 1, 1 over 2 to the s2 minus s1, 1 over 3, 2 to the s1 minus 1, I just canceled the 2 here, plus 1/3. And the term in parentheses is bounded by 1/2 because 2s1 minus 1 gives us at least 1. So we end up with 2 to the first. We get 1/6 at least, or at most, plus 1/3, and 1/6 plus 1/3 is 1/2. And so that means as long as s2 is strictly greater than s1. Now we know that s2 is greater than or equal to s1. We already had assumed that. So for strict inequality, we already get an upper bound of 1/4 times n minus 1 because we have a 1/2 here and a 1/2 here. That leaves case 3, 3a or something like that, the last case, that s1 is equal to s2. So in this case we have that 2 to the s times t is n minus 1, which is p1 p2 minus 1, which is, if I just add and subtract the p2, that's p1 minus 1 times p2 plus p2 minus 1. And that's 2 to the s1 t1, because that's p1 minus 1 times p2, plus 2 to the s1 t2, which is p2 minus 1. And remember, s1 is s2. And I'm just writing this out because we will need that to verify a step further down. And so that's 2 to the s1 t1 p2 plus t2, so that's just factored out. Remember that s1 was equal to t1 here. And that implies in particular that s1 is strictly smaller than s, because, well, it's smaller than or equal because this power must go into this power because t is odd. And then notice that t1, p2, and t2, they're all odd numbers. So I get odd number times odd number is an odd number, plus another odd number gives me an even number. So 1 power of 2 from this side is actually at least hidden in this parenthesis, and that means that s1 is strictly smaller than s. Therefore, the greatest common divisor of n and pj minus 1 is 2 to the s1 times the greatest common divisor of t and tj, independent of which j we choose, and it's really s1, it's not s. Now we can assume without loss of generality that p1 is greater than p2. Okay, that's where we have to be careful. We did assume something about p1 and p2 because we did assume that s1 was less than or equal than s2, but now we're in the case that s1 is equal to s2. So that assumption is basically gone, and the relationship here only depends on how t1 and t2 relate to each other, and so we can assume without loss of generality that p1 is greater than p2. And let us now suppose for a contradiction that the greatest common divisor of t and t1, which we also need in some ways, is t1. Well then, p1 minus 1 divides n minus 1. And that is because p1 minus 1 is 2 to the s1 times the greatest common divisor of t and t1. And so that would mean if that greatest common divisor is t1, then the greatest common divisor of these two numbers really is pj minus 1, because it would be 2 to the s1 times t1. So that means p1 minus 1 divides n minus 1, and then modulo p1 minus 1, we would have that 1 is equivalent to n, right, because that is the divisibility here. But n is p1 times p2, which is equivalent to p2 modulo p1 minus 1, because p1 is equivalent to 1 modulo p1 minus 1. And that would imply that p1 is greater or equal than p2, which is a contradiction, right? Because if a number is equivalent to 1 modulo p1 minus 1, then it's either equal to 1 or it's greater than p1 minus 1, and that would mean it is once, yeah, and that would mean that, okay, if p2 is greater than p1 minus 1, then it's greater or equal than p1, which is exactly what we want to avoid here. Of course, it could still be the possibility that p1 is equal to p2, but that would be a very quick quadratic test here anyway. Oh no, if p1 is equal to p2, we have that the exponent is 2, and that would already be ruled out. Okay, so that means that the greatest common divisor of t and t1 is smaller than t1, but that means that would mean that at least one factor of t1 is lost, and because t1 is odd, that means that the greatest common divisor is less than or equal than t1 over 3, right? Because we must have at least lost a factor of 3 as we went from t1 to the greatest common divisor of these two numbers. And that means the number of integers for which n is a strong pseudoprime to base b is at most, again, from the previous panels, it's going to be t, greatest common divisor of t and t1 times greatest common divisor of t and t2 times 1 plus 2 to the 2s1 minus 1 divided by 3. So we're basically picking up sort of where we left off in the last panel, only now we have to puzzle it apart a little bit more still. And what do we know? Well, we know that the greatest common divisor of t and t1 is less than or equal than 1/3 t1. We know the greatest common divisor of t and t2 is less than or equal than t2. 2 to the 2s1 times 1 over 2 to the 2s1, that is just 1, and we want that because we want to again pull this thing into this product back here, which we wanted to keep for a while. And so now what do we know here? Well, we keep the 1/3. t1 times t2 times 2 to the 2s1, that would be 2 to the s1 t1 times 2 to the s1 t2. Well, that is p1 minus 1 times p2 minus 1, so that's phi of n. And this last factor here is less than or equal than 1/2, and that pretty much comes out of exactly what we had proved before, because we had shown on the previous panel that this thing is at most 1/2, and so that's then bounded by 1/6, and that ends up being less than or equal than n minus 1 over 4, and we are done. And so basically what that means now, the reason why this is called a probabilistic primality test, is if we have a composite number, then the probability that n passes Miller's test with k randomly chosen bases, b1 through bk, between 1 and n, is 1 over 4 to the k, which means if I choose, I don't know, 20,000 bases randomly between 1 and n minus 1, then the probability that n will pass all these things, assuming that it's composite, the probability that it will pass all these tests will be 1 over 4 to the 20,000, which is 1 over 2 to the 40,000, and so that is just looking like it's very, very unlikely. We're in a situation here that is very similar to confidence intervals in statistics, because a confidence interval ultimately is an interval that goes from one number to another number, and therefore it will contain your answer or it won't. Just like our n is a composite, either a composite number or it's not. And so if I do this with a number and I run this test often enough, I haven't changed the probability whether the number is composite or not. But as I execute more of those tests and they are successful, you could say, like a statistician, my confidence that the number is prime increases. And so that is something we just have to be careful to make sure that the niceties and various formalities of mathematics certainly are observed. And that, well, that is Rabin's probabilistic primality test. Let's just finish this out now by talking about a few more primality tests. Basically, there is Lucas's converse of Fermat's little theorem, and that one says if you've got a natural number so that there is an integer so that x to the n minus 1 is equivalent to 1 modulo n, and x to the n minus 1 divided by q is not equivalent to 1 modulo n for all prime divisors of n minus 1, then the number n is prime. Okay, so I think the proof goes on one panel, and then we'll talk a little bit about what this converse does. Proof, well, so we know that x to the n minus 1 is equivalent to 1 modulo n, therefore we know that the order of x modulo n divides n minus 1. And it does so because x to the n minus 1 is equivalent to 1, yeah? And so now suppose for a contradiction that that order is smaller than n minus 1. Well, then there is a case so that n minus 1 is order of x modulo n times k. And that would imply that for some prime divisor of k, we have that x to the n minus 1 over q, which is of course x to the k times the order of x modulo n divided by q, is x to the order of x modulo n raised to the k over q, right? This standard trick that we have also seen a couple of times, that you pawn your denominator off to the more convenient part of the numerator. X to the order of x modulo n is of course 1 modulo n, and so the whole thing is 1 modulo n, and that can't be, because we have x to the n minus 1 over q is not equivalent to 1 modulo n. And so that means n minus 1 is the order of n of x modulo n. But the order of x modulo n, of course, is less than or equal than phi of n, and phi of n itself is less than or equal to n minus 1. That means that phi of n is equal to n minus 1, and that means that n must be prime, because only prime numbers are so that phi of number is equal to number minus 1. Okay, so that's the proof, and so basically this converse then in some, well, first of all, it's nice to have a converse, or if you wish, a partial converse, because we need additional hypotheses. But basically what it says is that if we have more knowledge about the prime divisors of n minus 1, then we can potentially also verify that n is a prime number. Now, if you work with huge numbers, if you work with numbers with 200 digits, okay, you know, n minus 1 is still a number with 200 digits, but it's even, so you can divide by 2, so, well, it still has 200 digits. But maybe that one then is easier to factor because you have changed, you change the number entirely, or maybe it has a lot of prime factors too, so you have a little bit of a chance again to use this as a primality test. That actually can be parlayed into a couple of things. So first of all, there's a corollary here. Take n and x be natural numbers so that n is odd, and x to the n minus 1 over 2 is equivalent to 1 modulo n, and x to the n minus 1 over q is not equivalent to 1 modulo n for all odd prime divisors of n minus 1, then n is prime. Well, that's basically Lucas's result, because x to the n minus 1 equivalent to 1 modulo n implies that x to the n minus 1 is equivalent to 1 modulo n, and that's what we needed for Lucas' test, because other than that, it just said that for the other prime divisors, which are 2 and the odd ones, we have that x to the n minus 1 over the divisor is not equivalent to 1, which negative 1 most certainly is not. So now we apply Lucas's result and get that that thing is prime. But basically then, when sufficient information is available, and that's something that I just took out of the textbook, and I'm not going to go into details, with sufficient information, and then this is parlayed with more sophisticated mathematics that is available to us right now into an honest-to-goodness test to check in O of log 2n to the 4th bit operations if a given number n is prime. So when sufficient information is available, it can be checked that way, and the explanation is basically if we can factor n minus 1, that's the sufficient information that we could say here we need. If we can factor n minus 1, then the number of steps taken to verify the condition in this corollary is exactly this O of log n to base 2 raised to the fourth. So that is something where I'll just refer you to the text here. The next test, however, and that's the interesting thing, that even though I felt like, yeah, okay, I mean, how much information can you get on n-1 when n is really hard and ugly? Well, apparently quite a bit, but then again, if you're looking for numbers that, for example, work really well for public key encryption, then you probably want n to be nasty and n-1 to be really nasty also. But either way, the next test also relies on some ability to factor n-1, which is and so the test is Pocklington's primality test. And so if we take a natural number n, so that n-1 has a factorization f times r, where the greatest common divisor of f and r is 1, and we want f to be the bigger factor. If then there is an integer a, so that a to the n-1 is equivalent to 1 modulo n, so that means that Fermat's test doesn't give us any information. But if then it's also the case that a to the n-1 over q modulo 1, greatest common divisor with that is with n is 1 for all prime divisors q of f, then n is prime. So again, we're reducing the check whether n is prime to checking other things that we hopefully know and using quick tests, such as greatest common divisors and modular exponentiations. Well, proof. Suppose for our contradiction that there is a prime divisor between 1 and root n of n. Well, then we've got the congruence a to the n-1 equivalent to 1 modulo n. That would mean that the order of a modulo p divides n-1, because if this is equivalent to 1 modulo n, then it's also equivalent to 1 modulo p, of course. And, well, then we take t to be so that n-1 is t times the order of a modulo p. And we take q to be a prime factor of f, and e the exponent of q in the prime factorization of f. So f is q to the e times more stuff. And let's suppose for a contradiction that q divides this t here. Well, then a to the n-1 over q, we're going to pawn stuff off again, right? That'll be a to the order of a modulo p times t divided by q. And if q divides t, then this quotient here is an integer, so this is a to the order of a modulo p raised to another number. So that's 1 modulo p. But that would mean that p divides a to the n-1 over q minus 1. That's what this one says, and p is also a divisor of n. And we're saying up here that that is not supposed to happen, right? And yeah, okay, so p divides this greatest common divisor, but we just said up here the greatest common divisor is 1. Well, p can't divide 1 if it's a prime number, so that's a contradiction. That means that q does not divide t, and therefore q, well, q does divide f, and therefore it divides f times r, and therefore it divides n-1. And so that means that q divides n-1. n-1 is t times the order of a modulo p. Well, if q doesn't divide t, q must divide order of a modulo p, and all the other powers must also go into the order of a modulo p. And because q was an arbitrary prime factor of f, we conclude that f must divide the order of a modulo p. Sure, if that works for one prime factor, it works for all of them. Then we put them together. But the order of a modulo p, because p is prime by Fermat's little theorem now, certainly says that the order of a modulo p divides p minus 1, and that means that f divides p minus 1, and that means that f is strictly smaller than p. And now we've got a contradiction, because we would get that n is strictly smaller than f squared, because remember that n has two factors and f is the larger of the two. F squared is smaller than p squared, and p squared is less than or equal than n because p was less than or equal than root n. And so that is the proof of Pocklington's primality test. So it's the kind of thing where I would think historically people realized, hey, if I know something about the factors of n-1, I can maybe make a dent and get a primality test out of that. And the last result for this set of slides, Prote's primality test, actually runs in the same direction. Namely, if you take a number n, well, another way to just split up an odd number is you split off a +1, and then you've got an even number, and you split the even number into a power of 2's times an odd number. So k and m are so that k is odd. And, well, then it's of course not always guaranteed that k is smaller than 2 to the m, but so basically that means that n minus 1 has enough factors too, so that we can make a difference. If there is an integer a, so that a to the n minus 1 over 2 is equivalent to 1 modulo n, then n is prime. Well, so we have n minus 1 being the product of two numbers, and the greater of the two is 2 to the m, so that feels very much like Pocklington's test, and in fact our proof is going to be that we will apply Pocklington's primality test. The reason why this test is still called Proud's test is because Proud's test predates Pocklington's test. In fact, right now, let me betray again my ignorance about the history here. I pronounce the name Proud the German way because I think he is German, but I don't know that for sure. But then again, unless he's British and not coming from any of the other countries that could name people Proud, well, only if he's British he would be named Proth. So maybe he was American. I really don't know. Look it up on Google, maybe. Okay, so basically we use Pocklington's test. We need an f, we need an r. Well, of course, we're going to use f being 2 to the m and r being k. And take an integer d, so that d divides n and d divides a to the n minus 1 over 2 minus 1. Well, then we know, because a to the n minus 1 over 2 is equivalent to negative 1 modulo n, we also have that any divisor of d divides the difference of those, so it divides a to the n minus 1 over 2 plus 1. And that means that d divides the difference of those two, but the difference of those two is 2. And because n is odd, that will mean that d must divide 1. And hence, the greatest common divisor of a to the n minus 1 over 2 and n is 1. And we know that all prime factors of f are 2, which means that by Pocklington's test, n is prime, because we have just shown that for all prime factors of f, namely for 2, we have that this greatest common divisor relation returns 1. And that is showing us that n is prime. Okay, we have gone through something that is pretty big, I think, at least from what I've read about it. Rabin's probabilistic primality test is apparently still a standard test as of the recording of these slides, so 2012, that is very much being used by people in prime number searches. So we have built ourselves in this course from basically the foundations of just knowing numbers, all the way to something that is quite sophisticated and current, and that certainly, I mean, that is very satisfying. That is a capstone for this course. If everything goes as planned, I will have one more set of slides, but other than that, we really are also going towards the end of this course. So that will, on one hand, probably mean that these results have exhausted you at least as much as they have exhausted me. This was really a good bit of work also for me to do, because I had never heard of Rabin's probabilistic primality test. For that matter, I had never heard of Miller's test, and just had to piece that stuff together for me. For any mistakes that have occurred on the slides, I certainly apologize. They come from my own inexperience, but at the same time, this one was actually pretty neat, because I don't think we had any significant mistakes there, except things like me being an analyst saying, well, if it's equal and I say smaller than or equal, that's not a mistake, that's just how analysts roll. Okay, take care of some homework problems, grind these things into your mind, understand what the proofs are, and I think I'll see you one more time in this course. Bye. We're going to do everything else in modular arithmetic, modulo primes and prime powers. And, well, Miller's primality test then basically fails to detect the number as being composite when certain power equations are solvable, namely b raised to a certain power equals to -1. And so the investigation of power residues will lead us to counting how many solutions such an equation can have, and that'll give us Rabin's probabilistic primality test. And we'll then at the end also talk about a few more primality tests as we slowly try to disengage from this pretty deep result, as far as I can see, for number theory, because we're going to use, to prove Miller's test, to prove Rabin's probabilistic primality test, we're probably going to use just about everything we've proved up to now, either directly or indirectly, in that we're going to use results that are derived from that. Okay, well, let's go. If we have two natural numbers, a and m, so that there is a primitive root r modulo m, and so that the greatest common divisor of a and m is 1, then we will call the unique integer x between 1 and phi of m, so that r to the x is equal to a modulo m. That number will be called the index of m. The index of ab to base r is the index of a to base r plus the index of b to base r, again modulo phi of m. And for all natural numbers, we have that the index of a to the k to base r is k times the index of a to r to base r modulo phi of m. And that is, of course, exactly like the logarithm laws that we know, except that we have to go in modular arithmetic, and that our modulus is phi of m. And, well, we're going to see why in just a second. And, well, it's very simple, right? R to the phi of m is equivalent to 1 modulo m. And because no smaller positive power of r is congruent to 1 modulo m, the index of r of 1 to base r is equivalent to 0 modulo phi of m. R to the index of a to base r plus index of b to the base r, well, we take that apart. That's r to the index of a to the base r times r to the index of b to the base r, which is a times b, which is r to the index of ab to the base r modulo m. And so we have r to one exponent is equivalent to r to the other exponent modulo m is 8 times 2 is 16, which is 5 modulo 11, times 2 is 10, and so we have 2 to the 5th is equal to 10 modulo 11, and the order of 2 has to be either 2, 5, or 10. It's neither 2 nor 5, so the order of 2 modulo 11 is 10, and that means it really is a primitive root modulo 11. And, well, so now, for example, since we can compute indices, the index of 10 modulo with respect to base 2 is 5 in modulo 11 arithmetic, because we've just counted our way through that, and we had seen that 2 to the 5th is equivalent to 10 modulo 11. Okay, well, let's take a look at some theorems. If we have a natural number so that r is a primitive root modulo m, so that basically just helps us sidestep the a little bit more cumbersome result that tells us when there is a primitive root. We just say m is one of those numbers. And we take a and b to be integers, so that the greatest common divisor of a and m and the greatest common divisor of b and m is 1. Well, then the index of 1 with respect to base r is equivalent to 0 modulo phi of m, not modulo m, modulo phi. Welcome to a capstone event in this course. We are going to prove Rabin's probabilistic primality test, which basically says that Miller's primality test that we already have talked about, which is actually a test to detect composite numbers, has only a limited number of false positives within the pool of bases that we can use to test. We will talk about that in more detail, of course, once we actually restate the whole thing. We need to set a little bit of groundwork first, because we have to talk about what basically is like logarithms in modular arithmetic, and that's what we'll start with. Okay, so basically these indices for index arithmetic, they play the role of logarithms modulo n. And so that also means that even without Rabin's probabilistic primality test, they're a natural next step as we are investigating modular arithmetic, because it's another piece of regular algebra that we'd like to carry over. We will use these indices to determine which numbers are power residues, and power residues, these things here, are basically just nth powers modulo m. And the theorem that we will have will only work when there are primitive roots modulo m, but that'll be just fine, because x, or the discrete logarithm of a to the base r modulo m. So that is exactly how we would want to define or exactly how we have defined logarithms in regular algebra. The logarithm is an exponent that makes a certain thing happen. we are going to use similar notation, except that we call it the index, not the logarithm. So it's called index of a to base r. And we're assuming that the underlying modulus is fixed. That'll require a little bit of thinking, because actually what's going to happen, because of this result that we have, that a to the I is equivalent to a to the j modulo m if and only if I is equivalent to j modulo phi of m under the right conditions. That result says that when we pull the exponents down, our modulus also will change from m to phi of m. We're going to see that. Okay, so as an example, well, 2 is a primitive root modulo 11, which means that 2 to the 10th is the first power that's equivalent to 1 modulo 11. And that'll mean that we can compute indices to the base 2 in modulo 11 arithmetic. Well, let's make sure that 2 really is a primitive root modulo 11. We can just count along, right? 2 times 2 is 4, times 2